Okay, so we're going to discuss the nested beta ansatz for the for this SU 2/2 spin chain. So the nested beta ansatz is this technology that kind of I think poses the one of the most major barrier for entering the field of interoperability. It's the thing that separates people who actually do interoperability versus people who only know it superficially. All right, so so first, let me just discuss kind of the general structure of the asymptotic kind of a beta wave function for a system of some particles, the m particles. You know, there will be some kind of wave function. This you can use some kind of one-dimensional quantum mechanical system. These particles will be the magnons of interest, but for now it's a kind of a general discussion. It's important here that so here we're going to be interested in a situation where, of course, the system is assumed to be integrable, but there are multiple types of particles. So before, when we write the beta ansatz, so even though we have written down the S matrix, the two-body S matrix, involving, you know, with this 10 by 10 components, right, 100 components S matrix, of the two-body scattering of all the components of these magnons, which is in the fundamental representation of SU2/2 times another SU2/2. And in actually solving for the energy eigenstates in the beta ansatz, so far we've only been using the simplest form of the beta ansatz, either in the SU2 sector or the SL2 sector, where there's only one type of magnon that's excited. But in order to progress to the mirror TVA, we're going to need to consider allow for all possible excitation. So for that purpose, we need to solve for the energy eigenstates with arbitrary magnon excitation. And that transition is more complicated than you might think. This is one situation where you generate, you know, generalize from one species particle to multi-species particle, kind of change the problem completely, and it's kind of quantitatively much more complicated. And this is what this nested beta ansatz is about. I did mention that there's a kind of quite a convoluted history of the nested beta ansatz, as far as I know. It's kind of supposed to be first discovered in this paper by C.N. Yang in the 50s, I think, or maybe the 60s, in just you know, some kind of integrable system of non-relativistic particle moving in one dimension. It was used. I mean, if you read the paper, you're not going to recognize any of the things I'm about to write. Now, this approach was employed actually in relativistic quantum field theory, integral quantum field in one plus one dimension, and it's used to solve the essentially the spectrum and form factors and all that for the you know, for the general OM model and Gross-Neville model in one plus one dimension. So, but it's also kind of independently developed in the spin chain kind of community. So let me write down the beta wave function. Phi psi A1 AM. These will label the particle type x1 and the xn. So here we're just writing down some n-body wave function, and we're going to write this in asymptotic region, x1 much less than x2 less than xm, and this wave function can write in the following form: sum over the plane waves to my asymptotic scattering states, e to the I p xj summed over j, Now P is the momentum of the J particle, and I'm going to write sigma J. Sigma is a permutation, sum over a permutation group, as n. And the coefficients are the components wave function, which will depend on sigma and depend on A1 of AM. So that's the general form of the wave function in asymptotic region. So it suffices to write this because you know of course this wave function is supposed to be symmetric with back to the permutation of the particles if you exchange the position and the label, the particle type label simultaneously. So it suffices to write this when the x's are ordered in this way. The conventions are related by S matrix elements, perhaps the most convenient way to express that is to express this in the language of the so-called Zamolodchikov Faddeev algebra. So this is something kind of once you write down, it's kind of quite obvious. So these coefficients, these C's are constrained by the scattering matrix, and the kind of most compact way to describe what a constraint is to write the following. Let me write this formula down and then explain this. So essentially, the idea is that roughly speaking, if I'm to permute the momenta of these particles, then the coefficients are related by the S matrix. Okay, let me not even try to attempt to draw a picture for that. So let's start with sigma being identity. So I write C1 for the identity permutation element. A1 AM. I'm going to introduce some creation operators. These are formal operators that will obey some algebra that will define momentarily. This is the so-called the ZF algebra, the Zamolodchikov Faddeev algebra. AM dagger PM. So think of this A as a creation operator for a particle. But the point is that these creation operators don't commute. That's the thing that's different from the usual kind of box space construction. Sum B1 the BM C sigma B1 the BM A dagger B1 B sigma 1 the A BM dagger B sigma M or any sigma in the permutation. Okay. So there's a relation like this, where the A's on the right-hand side, of course, I'm summing over the particle type label, but the momenta are permitted. And the A's are going to obey the following, so the ZF algebra relation says that A P1, A dagger P1, A dagger P2. But of course, I'm writing dagger just for creation operator. There is no non-dagger to A. So sum B1, B2, A B2, P2, A B1, P1. And the coefficient is the two-body S matrix element. S, which will depend on P1, P2, also depend on the particle types. A1, A2 of the incoming particle, and B2, B1 outgoing particle. So that's what it is. If we specialize to the SU2 2/2 speed chain, to say back to the left half of SU2, this little a will be the 2/2 fundamental representation of that super algebra. Okay, so using this algebra, you can arrange the right-hand side to put in the same form as the left-hand side. So that's a relation between the C coefficients. So you can work out what the relation between C coefficients are. So this is a general procedure to determine the asymptotic form of the wave function in terms of the S matrix element. So this is kind of really general for any integrable system. Now let's discuss the special problem. So we're going to put the system on a large circle of circumference L, okay? And we're going to say that we'll still have this wave function. we're still in the asymptotic regime here. So it's the some of the asymptotic kind of nested patterns. That's what we're going to be discussing. I haven't explained what does the word nested mean. That will come later. Psi A1 to the AM, X1 to the XM is going to be equal to psi A2 to the AM A1. That's permitted cyclically, and X2 to the XM, then X1 plus L. So this wave function is supposed to be periodic. That's how it's implemented at level of this asymptotic form of the wave function. So it's very easy to then see that. All right. So if you plug it into here, you'll find that this imposed relation on the coefficients C. A1 to the AM to be equal to e to the I P sigma 1 L C sigma T. I'll explain the notation in just a second. AM A1 for any sigma in the for segment M here. There's no N. And any permutation sigma, where T is the cyclic permutation 1 to the M. Okay, I mean these are kind of things you just have to sit down and check. I mean it's kind of hard to follow, you know, without actually just writing it out. Okay. So that would be the relation. Yeah, I mean, you know, yeah, to understand all of these things requires sitting down in a quiet environment and meditate. All right. So anyway, now if you plug into the if you compare this then with the ZF algebra, you'll find that it implies the well, let me yeah. So the ZF algebra would then imply the following. So let me write the intermediate step actually. So let's write C sigma T. Okay, so I mean, there's obvious transition of this where okay, you can compare the sigma, the formula for sigma with sigma prime. The sigma prime would be sigma T, let's say, and then you find that this one, B1 of Bm, can be written as sigma C sigma A 2 to the AM A1 okay, let me write this down and then explain it. It's a little hard to digest. 1, 2 times S C2 A3 P2 C3 P sigma 1 sigma 3 S C M minus 1 AM B M minus 1 PM B sigma 1 B sigma N. sorry. I think no. I meant this was A1 to me. I think it's just it's the same thing that appears. Yeah. Okay. This is actually kind of obvious. Okay, you have to keep track of the indices carefully, but it's kind of obvious because all is saying that if you compare the sum for sigma versus the sigma replaced by sigma t, they're supposed to be the same. The sigma t is where all the elements are shifted by one, and you can so this A daggers are kind of all shifted, well, kind of cyclically permuted by one, and you can return that to the same original order using the ZF algebra, but you have to kind of consecutively commute the guy with the p sigma 1 through p sigma 2 through p sigma 3, so you can pick up a whole chain of S matrix elements. But that's the procedure. So now if you take this whole thing, just set and plug into here, we get the equation just for the C sigma t. Now sigma is arbitrary, so you get a set of you get the equation for the same object, namely C sigma t. Okay. All right. In fact, it will suffice to for our purpose, it will suffice to restrict to a special case where erase some things. This is we're going to restrict to the case where sigma is e to the k is 1. Well, okay, let me actually skip this intermediate step. I don't think it's particularly illuminating to write this on the board. From this relation, I can, in particular, I have C1 the Bm is equal to e to the I P K L C1 K1 to the AM times a matrix TK, sometimes called the transfer matrix. A1 to the AM, B1 to the BM, for all K from 1 to M, where the TK matrix, A1 to the AM, B1 to BM is the following. It's something of that sort, the product of these two, a chain of two-body S matrices. So S PK plus 1, AK plus 1, BK plus 1, C2, S AK plus, sorry, C2, AK plus 2, BK plus 2, C3, PK plus 2, all the way to SCN minus 1, AK minus 1, BK minus 1, BK minus 1. Okay, so anyway, so you know you can it's not hard to derive from that. And then so this what this means is that you can think of this C1 with the A1 to the AM indices as a eigenvector with respect to the TK matrices. So this is some big matrix. It has you think the collective the A as the label for row and the B as label for the columns. And the TK matrices all have to commute with one another. Oh, well, sorry, not yet. It's a simultaneous it says that raise this and actually write some words down. This. It says that this C1 is eigen is an eigenvector with respect to T1 the Tm simultaneously. Now, first you can wonder whether this simultaneous eigenvector exists, but actually it turns out that the Ti, Tj is all commute. This follows from the Yang-Baxter equation. So you know, again, something that it's kind of elementary to check, but it is a consequence of the Yang-Baxter equation that the T's actually all commute with each other. So this makes sense. Okay. Now, so this is the asymptotic beta ansatz in the general form. Now, nesting means a specific procedure you're going to use to solve this. So in principle, you know, it's just a problem of solving some eigenvector problem, eigenvalue problem, some big matrix. The problem, though, is that for the practical application, we need to consider limit when m goes to infinity. Okay, so so you need some clever trick to solve this problem. You cannot literally diagonalize the matrices by hand. That's not going to be feasible. So that's what the nested beta ansatz is for. Okay. So we're going to describe now this nesting procedure. For this nesting procedure is going to this nesting procedure works differently for different symmetry group. So it very much depends on the type of symmetry group under which these index A will transform. Essentially, this kind of closely tied to representation theory of the algebra or the Lie group. Essentially, we basically want to grade these indices according to the weight of the state in the representation and kind of build kind of solutions kind of in the layers of kind of increasing or decreasing weights. Yes.
M is going to will take it to infinity, but the types of particle will remain.
Of course. The type of particle for us, but as you do such spin chain is always in the fundamental representation. So there's two statutes, so it's two bosonic, two fermionic. Okay, so yeah, I mean, in the literature, people in the past discussed like theories with ON or SUN, SUN symmetry. So that's where it's going to apply to the kind of ON or SUN, ON model, the gross number model. But now, from this point on, I'm going to specialize this SU2/2. There's some, I think there's some actually fairly deep representation theory when you kind of discuss the connection between, for given the algebra that govern this index A and the corresponding beta ansatz. I'm not really familiar with the story, but somehow there's some very deep kind of mathematics behind this, which I think like Kazakov, for example, has a lot of intuition about this, but which seems to be produce some results that seem to be kind of often magical. All right, so now let us specialize to the SU2/2. So in this case, remember this was only half of the symmetry of the spin chain, but it's easy to add the other half. So for the simplicity of notation, we're just going to focus on this left half SU2/2 for now. And the index A is going to, or A, all the A's, will be 1, 2, 3, 4. And our convention is that this corresponds to the boson and fermions, so called phi 1, phi 2, psi 1, psi 2. Remember this this var phi and the psi in my notes. These are not the actual boson and fermions of equals to superior mills. These are the left half of the fermion excitations, right? So if you take the left phi tensor with the right phi, then you get one of these four bosons that are in the transverse direction to the z's. to Z and Z bar. And if you take the phi tensor with psi, you get the fermions. And if you get psi tensor with psi, you get the covariant the gauge covariant derivative, right? Remember that relation. Okay, so anyway, but in any case, in the spin chain kind of language, we're gonna use focus for now on this left half of the Magnum quanta. So for example, so recall that okay, let me write this down. If we have only by one excitation, so this is what we mean this is what we mean by the SU2 section. If you only have the phi 1 excitation, then of course we know the Bethe-Ansatz equation. It's very easy to write. This is the equation that says e to the I pkl is equal to product j from k to m s pj pk, which s, well, this s is a particular scattering phase, right? So the s up here, this with ABCD, that's a matrix. In this case, I guess it would be a 16 by 16 matrix, which is of course unitary, provided the momenta in the physical regime. This S is by itself a phase, because if we only scatter phi 1 and phi 1, nothing else is produced. So that's the space by itself, which is what's required for this equation to make sense. Right? If it were not phase, it would not make sense. Now the idea is that we're gonna this phase, I will give it a new notation. I'll call this S1, 1. Well, the one in this in this kind of Latin numeral notation. So it indicates that there's some significance to this, right? So this will refer to we'll refer to this as level 1 excitation. So the level 1 excitation is what we call the usual Magnum excitation, but then we'll introduce level 2 and level 3. So there's a whole layer of new level abstraction. But let me explain some intuition before proceeding. So we started with a spin chain where we write the operator, the single trace, z and x, blah blah blah. So in the trace representation, you want to specify all the letters inside the trace. So this is what you can call the level 0 representation. The level 1 representation just means that you ignore the z's. So you say that it's mostly z's. In the sea of z's, you have a few magnons which are different from z's. So then you only discard them. You're only going to keep track of the magnon. You can forget about the z's. Just keep track of the position of the magnon, right? So that's the level 1 description. But now we're going to go beyond that. We're going to consider a sea of magnons on top of this level 2 excitation. And there will be a sea of level 2 excitation on top of this level 3. Okay, this is what the nested Bethe-Ansatz is going to be about.
Just to make sure, level 1 excitations only have Magnum by 1 or?
No. So if you just have 5, sorry. No. Okay. Well, yes and no. Okay. So the idea is going to be that so the general confusion magnons will be described in terms of simultaneously having level 1, level 2, and level 3 excitation. So if I have any magnon at all of this type, I'll say this is a level 1 excitation. But depending on which type it is, whether it's phi 1 or some other phi, I will say whether there's also a simultaneous level 2 excitation or level 3 excitation. So every single magnon gets elevated to some kind of auxiliary system of particles in level 1, level 2, and level 3. Okay. This will make more sense if I actually write down some formula, because this sounds a bit abstract and it's kind of hard to absorb. Yes.
If we had just phi 2s, we also be in the SU2 sector?
Yes, but that's not relevant to what I'm saying. So let me focus on the specific SC2 sector.
Okay.
Yes, well, technically we also call it SC2 sector, but let me not use that kind of language. Okay. There is more chalk somewhere.
So in that, absolutely.
Oh,
In that
which
box.
ping? In which box? Oh, this box. Ah, good.
Oh, okay. So, whatever. Um, okay. So anyway, so this S for now is going to represent the level 1 S matrix element, and the idea is that essentially we want to diagonalize this problem, and so we do not want to work with S matrices that are matrices. We want to work with only scattering phases. So this whole nesting procedure is going to be procedures to solve this eigenvalue problem by turning this non-abelian problem into a abelian problem. Okay, so that's where we're aiming at. So this guy is the level 1 scattering matrix, and of course the actual scattering phase is something you already know. This is what we called A12. So this thing, so S where this S11, P1, P2 is this matrix element we call A12. Remember we have A, B, C, D, E, F, G, H, I, H. Well, anyway, yeah, there are like these 10 matrix elements. This is literally the first one of those. I'm not going to repeat the formula, but you remember this involving the expression involving x plus and x minus, which is kind of impossible. Well, it's kind of impossible to remember, but I look up the formula in the notes. Okay. So. Now the scattering state, we're going to use the following notation. So of course, this equation applies to just the state with phi 1 excitation. That state, I'll write the following notation. Phi 1 P1, phi 1 PM. I mean, first, this is the notation I have been using, but let me put the label 1 here just to emphasize that this is the level 1. So level 1 is this thing, the sort of thing we have been doing all along. Okay. And of course, just to be kind of maximally explicit, this in the language of the wave function, this asymptotic wave function, this corresponds to C1 A1 the AM to be delta A1 1 the delta AM 1. So this is just as all the particle type has to be equal to 1. That's nothing fancy. Okay, good. Now, our procedure, nesting procedure is going to be that this thing is going to become the vacuum of level 2. So the solution of the SC2 sector now provides the vacuum, the starting point for the level 2 discussion. So the level 2, we're going to replace some of the phi's with psi. So let me give you an example. So level 2 will be let's say level 2 excitation. Will replace some of the phi 1s with psi alpha or phi 2. So this is under the assumption that the total number of magnons is fixed to be m. We're just going to fix that. Right? Of course, private part of the number is conserved in the indoor scatterings problem. So for example, let's consider a single excitation, psi alpha y 2. We want to construct, well, we don't want to just talk about some excitation, we want to construct something that's going to be eigenstate of the Hamiltonian. So we have to come up with some suitable ansatz for this. What is y? Well, I haven't defined what y is. So y is some, I call a level 2 spectral parameter. I mean, it's going to be you see, originally, at level 1, I wrote this as function momenta. That makes sense because the set of momenta is conserved under scattering. The momentum get exchanged, but they don't, but the set of momenta doesn't change under integral scattering. So for an eigenstate, I can talk about this, the actual values of P1 through Pn. Now, in order to describe the level 2 excitation, I cannot parameterize this in terms of any specific momentum. So let me write down the example of what a single particle excitation level 2 means. So I need to consider the combination of the level 1 state by 1, P1, all the way to phi 1, Pm. Pm level 1, but in the middle, the kth entry is replaced by psi alpha pk. But only that entry. Okay. So that's what it means to have this level 2 excitation of a single psi particle. I need to take a linear combination of this. So k from 1 to m, ck y pj. So the ck, you can think of this as sort of the level 2 wave function. So this is a new object, right, which we have not encountered before. It's going to depend on the pj's and depend on some yet unspecified special parameter y. I can choose some convenient parameterization, which we'll specify shortly. Okay, so yes.
This state on the right-hand side, which is a level 1 state with a psi in it.
Yeah.
Don't we already have to solve some conditions on these C's where one of the A's is now 3 or 4, I guess?
No. This is we have defined. We have defined this.
We have defined that one, but
No. Before today, we have defined exactly what that state means.
Oh.
Okay, maybe I should have said that here I'm talking about the in-state.
oh,
Yeah, let me be careful, right? I'm talking about the in-state when the particles are ordered in this particular way.
Okay.
So that stands for the scattering in-state. Let me. I think I'm going to write something that will clarify this. I'm going to write the actual wave function of this in the original this C sigma A A1. I think that will help clarify this. I only need to write C1 because all the other C sigmas are related by the ZF algebra. So C1 A1 AM Pj is equal to sum over k ck y pj delta a1 1 delta am 1, but delta ak well, in my convention this is delta ak alpha plus 2. I mean, I'm using a very stupid notation just because the index range from 1 to 3, 4, and the alpha equals 1 and 2. So psi 1, psi 2 means 3 and 4. Okay, so that's just the convention, right? But that's it. I'm not doing anything fancy, right? I literally talk about this. So you can think of the C1 as describing the in-state wave function, and it's what it is.
so just to be correct, the C1 for let's say one chosen K is just that combination of deltas where.
For one chosen K, there's no such thing as one, what do you mean one chosen K? You have a sum over K here.
Yeah, I'm saying, okay, that state on the right hand side that you said we already. This,
Oh, yeah.
That
That's
the
right.
C1 of it is just. the
That's right.
part.
That's right. It's simply that, there's nothing more. Yeah.
So why cannot I just take the spectral parameter to be the momentum, what it goes wrong? Like,
Why can what?
why isn't the spectral parameter like just the momentum, what goes wrong? I didn't quite catch it.
It will not be determined just by the momentum. It's not determined by the momentum because you see that you can everybody can put a sign in different places while trying to take some near combination, right? It's more than, you know, the state is not just labeled by P1 to dot PM.
Okay,
There's more data.
I see.
So that's why it's supposed to keep track of the extra data.
Yes.
Good. Any other questions? It's kind of an essential point of the construction. Now, well, this is not enough. We actually have to solve for this wave function. We need to solve the condition for the energy eigenstate. So here comes the actual crucial step, which is that, you know, in any integrated business, you are always encounter this kind of problem of, you know, some kind of eigenvalue problem, and you're going to guess the solution. You're going to guess an ansatz that's going to solve, and then try to see if it works. It turns out this problem can be solved completely. You can determine what the CKs are because of some integrated magic. But let me explain how that works. I think because this is, in some sense, this is sort of the single most crucial step. So I'm going to take the CKY Pj is equal to product L from 1 to K minus 1 S to 1 Y dl F Y dk. In fact, just to be clear about the language, I think yeah, in some sense you can think of okay, I guess I'm not sure what the standard terminology for what this CKs are. If you refer to CK as some kind of level 1 wave function, this F is going to be a level 2 wave function. But for now, let's just about this ansatz. So there are two objects here I haven't defined. There's some function. They depend only on the variable that I have exhibited here. So that's ansatz. So there's a function F, which is some kind of a higher level wave function. And then there's this S, which is a new object. This is a new scattering phase between a level 2 excitation and level 1 excitation. Okay, so the idea is that we're gonna resolve this magnon into, like, you know, some kind of abelian object at multiple levels. And we have already introduced this level 1 S matrix. They're going to be a level 2 level 1 S matrix. Well, when I say S matrix is a single scattering phase, that's going to be very important. So far, it's not obvious why this ansatz work, right? We're going to have to check that it actually works. There's some intuition behind this. I mean, I don't really have a good way to explain this other than just kind of playing with the equation. It's started long enough, you see that something like this might work. But let's actually try to determine them.
Just to make sure that I understand this formula. So now we have the state psi alpha, but this CK does not have like an alpha index. Does that mean that, like, if we replace the psi alpha by phi 2, the
No. This alpha refers specifically alpha is 1 or 2.
Yeah, I'm just saying if this wave function CK is universal for all the psi alphas, or it's like specific for this psi alpha.
The CK is universal to the extent that it depends on the special parameter y, right? Obviously it's independent of alpha because alpha 1 and alpha 2 they're related by symmetry. So the same thing applies for, so it doesn't matter whether it's alpha is 1 or 2. That much is clear. Yeah. Okay. So this is the ansatz. So this is a guess. Now let's see if it works. Oh, actually, sorry, there's one extra step. We also need we'll see the following. So let me see. We also need to say that C sigma A1 the AM EJ. Okay, so this step is just as crucial. C1 A1 AM P sigma J product JL in the index set I sigma, define that in a moment, SI I mean the level 1 S matrix PJ PL, where this I sigma is the set of pairwise permutations of neighbors that brings A dagger P1 to the A dagger P. Let's call it A1, A dagger PM to the one that's permitted, A P sigma 1 plus A1 dagger P sigma. Okay, so let me try to give some kind of intuition for this. So I mean, ultimately, this is just something you have to check. But heuristically, you can think of this as saying that if I, well, that's literally what it's saying, that the different kind of asymptotic region of the wave function are related. By this level 1 S matrix in this particular way. This is actually, let me see if there's a. I always find this kind of hard to actually understand. It's something that you can check that it actually works, but the intuition of why you are allowed to a priori impose this is it's a little hard to understand.
It just follows from the ZF
No, it does not. No, it does not. I want to emphasize importantly that this is a guess. Okay, these are scattering phases. The ZF algebra involves two body S matrix elements, which are matrices. That's completely different from this. Okay. Yeah.
When you say the set of pairwise permutations, you mean like the sequence of pairwise permutations that would effectively.
No, I don't have to specify the sequence because the order that doesn't actually matter because
Okay, I'm saying they're the set that if you put them in.
Oh yeah, that's right. That's right. That's right. That's right. Yeah. Let me see if I have. Also, this region actually reads very funny because the ZF algebra tells you some it's some kind of relation between C1 and the linear combination of C sigma for all the different indices, different particle types. But here I'm imposing this for fixed set of particle types. So this is a bit weird. Okay, but Now, yeah, in fact, I don't really have a good way to explain intuitively why you're allowed to impose this without actually checking the equation. But let's plug this into the equation. So yeah, these two ansatz, this two part of the ansatz is kind of the single most crucial step actually. Okay, so it's useful to recall this equation that says sum C1 A1, sorry, A dagger P1 PM. This is let's recall this equation. P1, not bother writing this. So sigma A dagger P sigma 1 dagger P sigma M, and with the this P1 yeah. So plug into that equation. So in particular, let's put this in here. All right. So and that the C1 is this. Right, so can I express the C1 in terms of the CKY, depending on the special parameter Y, and then blah blah blah. So here's what you find: sum over K, CK, Y, PJs, A1 dagger P1, A PK gets replaced with alpha plus 2. This is the thing that represents psi, A1 dagger PM. Is equal to this product J L, this index I sigma S11 PJ PL. Over K CK Y P sigma J A1 P sigma 1 A alpha plus 2 P sigma K A1 P sigma. Okay, so now the question is, can we solve this equation? Of course, we'll be able to solve it, otherwise I would not be telling you this ansatz. But it's not obvious, but still not obvious at this stage. So to solve this equation, actually, it suffices to consider the sigma being a pairwise permutation, and then you can just compose it and get all the rest. So let's consider sigma to be permutation between neighboring sites M and M plus 1. Okay, so here comes the okay, so here's where you're going to use the kind of nice structure of this ansatz. Let me see if I can something that's already easy to see here. Right. Okay. So earlier you might wonder why I choose this specific ansatz of this form. Okay. So here's where you benefit from it. You see, if sigma is a permutation between the neighboring sites M and M plus 1, let's just imagine a situation where there are many of these A daggers, right? So the sigma does not touch anything. So you have any particles, then you have m plus one. So sigma exchange these two. It does not touch the rest. So from one all the way down to capital M. Does not touch those. And okay. Let me say this in the nicer way. So in particular, maybe this is not even the right. Okay, maybe let me not actually draw this picture. This is not the correct. It's not a good way to represent what is going on here. So if you look at this expression, the sigma does not touch. Okay, so for the entry that is not m or m plus one, sigma does not touch it. Right, so the A dagger on the left hand side and on the right hand side will be the same. When the sigma, so if this is the case, actually you only have a single S matrix, single scattering phase here, and what it does is the following. So if you're looking at the entry in this equation, so the sum over k, if k is far away from m or m plus one, then this equation is automatically taken care of by this phase in front here. Because if k is far away from m or m plus one, this permutation doesn't touch this weird A assertion. It only touches the A once. Kind of a pair of A1 gets permuted. And then you can use the ZF algebra to put it back to the left-hand side form just up to this phase. So that's what that phase is for, right? So by the choice of this phase, this equation is automatically satisfied for the terms where k is away from m or m plus one. So you just need to check the equation where the k is equal to so the only non-trivial equation to check is when it's for let's say k is equal to m or n plus one. Okay, and in fact, it doesn't even matter what the value of m is. M can be 1 or 2 or 3. It doesn't even matter. So for example, let's look at m equals 1 case. So so in that case, the equation boils down to the following. Here, I am going to need then to use this representation of CK. I'm going to make explicit use of that. So let me write it. Yes.
Should the CK on the right hand side be C of sigma k?
No.
Well, I thought the size now has P of sigma k, and on the right hand side, the onset CK singles out the PK.
Let me see. Sorry, you want to write what?
The CK in the sum,
What about it?
I should be C of sigma of k.
There's no such thing as sigma. What do you mean? No. That's no. No, there's not. Why? There's no reason. I'm literally using this formula and just plugging in.
Well, I'm looking at the top line there, the CK of YPJ. The only place K appears on the right is as the subscript of PK.
No, it's the kth entry here. This is the kth entry.
The kth entry of a sigma kth.
The kth entry. Absolutely the kth entry. Not the sigma kth entry, that's the whole point. You know, the B's are some arbitrary label. I can just call this P prime J if you want. There's nothing to do with this kth. This question is correct.
So that CK, the momentum that it singles out for F is not going to be the size.
But this is literally what you get by plugging this in.
Okay.
As I said, all I do is I replace this with 3 sigma j, and then it's the same formula. Okay, it's not touched. I'll just give you a minute to stare at this, because indeed, this equation is not very easy to absorb. We really have to just you know, when I play with this, I find that you know, I personally have limited intuition about this. You just have to work out the algebra, like you know, it's these things are, you know, it's impossible to remember any one particular equation. That's the nature of this game. Like if I didn't derive this from the scratch, I would not be able to just produce any one of the single equations from the middle. So it's like it's kind of impossible. Yeah. Now, I should mention that you'll find that this formula, okay, maybe I should also mention some references. The first place I see the formula presented this way was in actually the Beiser 2005 paper. That paper gave kind of a clean derivation, which is basically what I'm sketching here. Well, it's basically to as much. Actually, what I'm describing here is in more detail than was given in the paper. I mean, the idea that it can kind of organize this according to these levels for this particular system was already noted in the earlier paper by Beiser and Staudecker. But I think usually with this kind of thing, you know, I think even for them, they just have to. They kind of know that something like this will have to work, but the details of this cannot, you know, get this from any reference. You just have to work it out following the kind of the general idea. Because they refer to in this Beiser Staudecker paper, they refer to Xian Yang's old paper, which is in a completely different language. It's not possible to directly translate. And also there's some book, and this book, I think what was it? Well, a Hubbard model, and you know, it's also it's kind of impossible to directly translate. Okay, so so anyway, that's sort of the only place, that's sort of the first place I've seen it formulated in this language I'm describing here. And you'll find some like later papers in the context of ADS-CFT spin chain where these kind of manipulations are analyzed. I think all the relevant references are actually given in the footnote of my notes. Because, you know, in my notes I gave some of the derivations, but not like complete detail, because some of the formula is just too long. You have to write like several pages of, you know, solving like some matrix equation. If you want to like have all that written out, it's not going to be particularly illuminating. But let me at least demonstrate the simplest non-trivial case, which is the one I'm about to write here. So Fy E1 you know, one of the things about the integrability is that you also have to work very hard. I mean, you know, it's right that you have all this elegant underlying structure, but in order to unveil the structure, you have to do a lot of calculations. There's kind of no way around it. So in the Beiser 2005 paper, you know, like the paper is not too long, but actually there's a huge amount of calculation that goes into the derivation that's all like kind of hidden away because you just kind of essentially state the results. Let's go to. Okay, so first let me see this. So what I'm saying here that okay, so these are going to be the two terms that are relevant. So here it suffices for the k to sum up to 2. So those are two terms that are Wait, okay, sorry, just a moment. Myself confused about something. One. Right. So, actually, let me finish writing the equation and then try to explain. It's two, sorry. It's one, U1, U2. F Y2, a dagger plus 2, P2, a dagger 1, 1. Y1 is 2, 1, P2, 1, P2, 2, 1. Let me make sure I didn't make a typo here. Just a moment. It wasn't something I'm writing here. No. It's correct. Yeah. Okay. This is hard to me to recall in real time. Okay, so this is correct. So let me explain this. So this is sort of the simple natural case, but the simple natural case is always the most important case to understand. So here it suffices to check the equation for the sum just k up to 2, because that's the part that's not trivial. The other term will get cancelled by construction, by design. So when k is equal to 1, so the way I'm writing here is funny. That's the thing I confuse in a second. If k is equal to 1, this means that this is the first entry. So that's this term, right? That's that term. And I'm putting this f here. This f just comes from this, and there's no further phase. The next term I have this funny phase over here. That's the 2-1 phase. This phase is yet to be determined. Okay. And then on the right hand side, I have this. I just copy down here, and I have the same thing, but with the P1, P2 swapped. And the P1, P2 swapped because of sigma. And that's it. That's the equation. Now this equation looks already very interesting. Well, this is in some sense like one of the most non-trivial equations. Once you understand this, the rest it's just a generalization. So if you start this equation, now you observe that, of course, you can you can relate this to this, of course, by the ZF algebra. So let me describe the solution to this equation. You see, the ZF algebra. What is it? Okay, I need to erase something to make space so that I actually can like this. I think I no longer need this next equation. So let me erase the next equation here. So we can rewrite this and this. So the right hand side can put it back to the left hand side form. You apply the ZF algebra to this. Right. The result of ZF algebra is like you take the two particles and you scatter, get the combination of this particle of this type and that type. You see, the parallel type can get swapped because here you have a phi and you have a psi. When you scatter, you can have psi phi or phi psi. Okay, so each of these by the ZF algebra is going to be a linear combination of these two. The coefficients involve some of these 10 matrix elements I've written before, A, B, C, D, E, F, G. So we'll have, they'll involve G12, H12, K12, and L12. You can look up the formula for what these things are, but these are going to show up in re-expressing these as linear combination of these two terms. But then, of course, these two are linearly independent objects. So you get two linear equations for two unknown functions, f and s21, and you can solve them. Okay, so this is where the magic occurs. All right, so you can solve them, and the solution is okay. So what is the equation? Let me write this down because this is kind of the most crucial step. I think I no longer need this equation, so I can erase this now. What does the equation look like? It looks like this: f y p1 l12 plus f y p2 s21 yp1 h12 equal to s. Oh wait, I have a typo here. Oh no, I think it's correct. It's correct. Yeah. S21, YP2, FYP1, and A12. The A12 is this S11. I'm using the expression S11 is equal to A12. That's one equation. Another equation is FYP1 K12 plus FYP2 S21 YP1 G12 equal to FYP2 A12. Okay, so now we can solve, and the solution are the following form. So FYP equal to some, so AP over Y minus X plus P, where AP is a quantity that appears in the in this matrix elements. Let me see, call the definition of this object. Well, I don't know if I want to. Okay, let's see. Place where I wrote specific expression before again. Find the formula. Yeah, so remember, as a long time ago, this was probably like the first or second lecture. I had this ABCD, which is a function of P that AB equals K, CD equals K star, AD minus BC equals 1, and AD plus BC equals H for the single magnitude dispersion relation. So these ABCD by themselves also enter some of the matrix elements. So this is the one that enters one of these G or H or L or K. I forgot which one it is. I think actually it's probably like H and K. Anyway, it's something that is a function of the momenta that is it's known and enters these S matrix elements due to the SU to go into a constraint. Let me finish writing the solution. So so F is of this form, and S21, you have to solve them simultaneously. S21 YP is equal to Y minus X minus P, Y minus X plus P. So there's some magic that has occurred here that leads to a kind of a dramatic simplification of the solution. so you see, up to now, I haven't told you what y is. Right, I told you that y is some special parameter. So this is some kind of weird functional equation. And what I'm telling you is that the solution is of this form. So y is whatever you want it, you choose to be, but but here I just choose y to appear in the equation in the solution in this way so that it's convenient parameterization. I mean, I could replace the y by any function of y, it doesn't matter. Same thing. The statement is that, for any given constant parameter y, constant y, let's say, this will solve the equation. And the most general solution is of this form. Okay, so this is some kind of magic. And of course, here it's remarkably simple because these things are kind of complicated, but the solution is remarkably simple. So once you see this, you know that you're doing something right. Okay. Now, the interpretation of this is going to be that, as I said, this S to 1, you're supposed to view this as a scattering phase between a level 2 excitation and level 1 excitation. Now, these are not different magnums. You should think of this as all part of the same kind of magnum, but the one magnum gets it's like some kind of resolution. It gets lifted to like a billion objects at multiple levels. Later, I will write what the actual beta-ansatz is in terms of these different level parameters. But the idea is basically going to be that a general magnum. You want to think about the magnum as an entire multiplet. And this multiplet can involve level 2, level 1, level 2, and I will also say about level 3 excitation, which will be labeled by this momentum, but together with some special parameter. Yes.
Somehow this is so simple just because it takes care of the kinematics, whereas the dynamics was already at level 1. Is that somehow true? Because this sort of abletonizes this non-abelian as you do.
I mean, all of this, of course, is somehow a consequence of the symmetry, the SU2 such symmetry, right? I mean, that is certainly true. That is certainly true. So all of this somehow is to kind of unravel the symmetry constraints that relate the different components of the two-body asymmetry.
Because the expression at level 1 was much more complicated, right? This is like much simpler, I think.
That is true, but the more complicated thing is also a consequence of just symmetry, apart from the dressing phase. So, but anyway, the intuition here is that you want to think of this y as a special parameter, just like the p or the x plus and x minus, but now for a level 2 excitation. And so you think of this as some kind of level 2 excitation that scatters with level 1 particle. Now, I don't know any kind of analog of this in any other areas of physics. This is some level of abstraction that I've only seen in this kind of necessary beta-ansatz context. And this fypk is some kind of higher. You can think of this as a higher level wave function. So for this level 2 excitation embedded in this C of level 1 excitations, which is now viewed as level 2 vacuum. Okay. All of this was just the one particle state level 2. The next thing I'm going to discuss is 2 particle state level 2. Once you have 2 particles, you have n particles, right? I mean, we're doing integrability, right? So you just need to understand 2 particles. So we need to understand the 2 particle state level 2, which will involve scattering between level 2 excitations among themselves, which so far has not appeared because so far we're only talking about level 2 excitation with a single level 2 particle, a single level 2 excitation. Yes.
Is the level 2 specifically for the size? You mentioned phi 2, but I thought, for example.
Yeah, I'll come to that. So roughly speaking, the phi 2 is like a bound state between the 2 sides.
Okay, because the phi 2 can scatter off of phi 1 to make the size.
Yeah, so the phi 2 will be on the equal footing as a pair of sides. So we'll come to this momentarily. That's going to be the point. So once you discuss the level 2 excitation state, which means 2 sides, you'll mix with a single phi 2.
So that's kind of the reasoning why we start the level 2s with the size instead of.
That is correct.
Because otherwise we wouldn't be able to kind of.
That's correct. So this phi, I mean, this is kind of obvious from the group theory point of view because with back to SU2, the weight,
Right.
The psi has a sort of a smaller weight, and then you can use them to build the phi 2.
Yeah, but if we start with phi's in this boxed equation on the left, we would end up with a different species of A's on the left and the right.
Yeah, you have a problem because you're not gonna be able to diagonalize the Hamiltonian using a single phi particle because it's gonna mix with psi. That's exactly right. I should mention, however, that there is an alternative approach. Instead of starting from this H2 sector phi1, I could have started with psi1. And then the phi1 and phi2 will be the same. So this will be actually used for some purpose. I mean, they're ultimately equivalent, but they're kind of different representations of this resolution or this nesting procedure.
And starting level 0 with phi1 instead of phi2 is just the arbitrary.
And that's a choice, yes. Okay. So now we'll discuss level 2 scattering. One third. The level 2 scattering. So for now, for this, we need to consider the following states. So I think I can erase all of this explicit beta function stuff. This is just to illustrate, what is really going on at the level of the actual asymptotic wave function of the magna. But now we're gonna write. Let me also, now that I have solved this, I'm also going to erase all of this. Psi alpha, y1, psi beta, y2. You should think of this as also in-state. In-state basis. We're going to consider. Okay. This in-state basis is not going to be okay. More space. So this in-state basis I'm about to write is by itself not a eigenstate of the Hamiltonian, right? So the level 1. So by construction, the level 2 1 excitation state was eigenstate by construction. That's what I showed earlier. But for the 2 particles, you still have to you have to find the appropriate wave function. So right now I'm writing the in basis for the 2 excitation level 2 states. And once I write on this basis, we're going to discuss how to find the asymptotic wave function that actually diagonalizes the Hamiltonian. So here, write like this. So I have a psi alpha y1, psi beta y2, and level 2. So this is defined to be sum k from 1 to m ck y pj y1 pj y2 pj. So remember, the y is a special parameter, which is now like kind of labels the quantum number of level 2 excitation, like the spectral parameter for the excitation. And we're just going to have psi alpha here and the psi beta for the alpha end. That's that. And as I said, we also need this phi 2, which will mix. The thing you have to be careful about is that you need to insert the extra z so that these 2 things are appropriately related by supersymmetry. This is the reason why advisor calls it the dynamics being changed. The length can change. We'll write this as some ck y1 j ck y2 pj times some yet unknown function f y1 y2 pk phi 1 1 the phi 2 pk. This means the kth entry gets changed into phi 2 pk z plus, is inserting a z, and then the rest are still phi 1s. This is again an ansatz. I'm assuming that this phi2 depends on this two spectral parameters y1 and y2 through some function, some kind of wave function. I guess you can think of this f as some kind of a bound state wave function. Yes.
Should the first equation be a sum over K and L instead of?
No. Oh, sorry. Sorry. Thank you. Yes. K and L. That's right. I meant to write K less than L here. Yes. Good. So now our ansatz for the energy eigenstate is going to be of the form. So the energy eigenstate, this part is say psi, capital psi. Well, what can it be? Well, the particle numbers are conserved, so it has to be some determination psi alpha y1, psi beta y2, level 2, plus epsilon alpha beta by symmetry, phi 2, y1, y2, z plus 2, plus s, I'll call this just s2. We'll discuss what they are momentarily. Alpha beta, delta gamma, y1, y2, psi delta, y2, psi gamma, y1, level 2. Well, this S is S2 is some two-body S matrix level 2. Now, whatever it is, it has to be invariant with back to this appropriate SU2 symmetry act on the index alpha. So this S here, this expression is delta alpha delta beta gamma m y1 y2 plus delta alpha gamma delta beta delta n y1 y2. So the level 2 two-body asymmetry elements. Okay. Now, the condition for the eigenstate equation, it's by the same invention as before. You go back to the asymptotic beta wave function, and you'll find that again this this ansatz is such that the only natural case to check for the eigenstatic condition is when m equals to 2. And if m equals to 2, you can just write this out in terms of that. And it again becomes a kind of linear algebra problem. You have to solve some a bunch of linear equations for that will determine these functions, the unknown functions, which are n y1 y2, n y1 y2, and f y1 y2 p. All right. So I gave all the solution. I gave all the formula in the notes. I don't think it's particularly illuminating for me to write this down. I mean, actually, okay. Let me actually write it down because you can see this at least once, so that you kind of recognize the pattern. It's kind of important. So what are these? So what does the solution look like? So m plus n equal to -1. This is actually obvious. This is because if you set all the set alpha and beta to be the same, there's no scattering between the well, apart from the fact that these are fermionic. N minus N. Okay, so maybe there's a better way to say this is that you know, you can of course decompose this with vector irreducible representation of this SU2X on the alpha and beta indices, right? So you get a triplet and a singlet. So the triplet part is kind of trivial. So that corresponds to N plus N equals N plus N. The non-trivial part is a singlet. And the singlets, this N minus N, which is the controls the singlet S matrix. It turned out to have some weird formula like this: y1 plus 1 over y1 minus y2 minus 1 over y2 minus I over h y1. Remember, this h is the square root of the tooth coupling. That's the thing that enters you know, the relation between x plus and x minus. So this will show up here. You know, these are the kind of things in integrability where, you know, when you play this equation long enough, you get some intuition, but other than just playing with the equations, this would seem, you know, for someone unfamiliar with the equation, this seems to be just some random formula. So I want to emphasize that this y1, y2, these were the spectral parameters that I just defined earlier. They are the ones that show up in these expressions. Oh, sorry, this is supposed to be 2 ones. Right. So the y's were just by definition the ones that appear here, but then they feed into the equation for this S2, and it turns out that the singlet part of S2 is this kind of function of y1 and y2. And there's also a formula for this. This is kind of law. Let me not write this. This scattering phase will be important because this is going to be sort of a non-trivial level 2 scattering phase. In fact, I think at some point I will introduce a how should I put this? Let's see. All right. So here, now that we have this level 2 two-body estimation element S2, this S2 will help us now define a level 2 ZF algebra. So using a level 2 ZF algebra, we'll be able to write a ansatz for the n-body eigenstate wave functions. That will look like the following. If I'd like to make another comment before I continue. So, as I said, so here we have what we have just solved is essentially some kind of you know, just a two-body scattering problem at level 2. The elementary quanta are this size. This phi 2 is describes basically something that happens when the size kind of come together, right? So, but if we're to describe asymptotic wave function, where the sides are far separated, then there's no phi 2. Right, so the asymptotic wave function will just be the size. This phi 2 is some object that will participate in the full wave function and describe what happens when the pair of size come together. So it's necessary to keep track of size phi 2 to solve for this S2. But once you have solved the S2, you can now discuss the asymptotic wave function just in terms of the size and using S2. And somehow a kind of a common experience with the integrability business is that thanks. One of the experience with the integrability business is that when you kind of very often when you work out the kind of asymptotic from the wave function and so forth, it kind of also works away from the asymptotic region. It doesn't always work, but very often it works. And the philosophy of integrability kind of approach in general is that you assume that it works and proceed and check and run the problem rather than trying to prove it. Only for the reason that it's not like we don't care about proving it. In fact, some mathematicians do care very much about proving such things. But as you can see, the technical details are so complicated that usually you're not at the stage where you have the luxury to afford to try to prove. You just want to calculate and see what the answer is. That's the nature of subject. So maybe like some decades later, someone can try to prove it, but to begin with, you just want to find the answer. That's what we're doing. Okay, so let me write down the general level 2 scattering state. It'll look like this. So I'm going to just write the asymptotic wave function. So this means that the sides are far separated from one another, so that we don't have to worry about this phi 2 component. So it looks like the following. It looks like some sigma sk, where k is the number of level 2 excitations. So remember, I use the notation m for the number of level 1 excitation, which is the actual number of magnons, and k it will be the number of level 2 excitations, which is of course less than m. Sum over alpha 1, alpha k, d sigma. So earlier I wrote c, now this is d. This d is similar to c, but now at level 2. Sine alpha 1, y sigma 1, sigma, sorry, alpha k, y sigma 1. Remember, y has replaced momentum as the special parameter for the level 2 excitation. So you can look at the formula in the notes. Let me not repeat this on the board. So these sigmas are related. I'll just say this in words. Are related by a level 2 homological Faddeev algebra. Then this just means the homological Faddeev algebra determined by this S2. That thing, S2 alpha beta delta gamma. So it's just like what we discussed before about the asymptotic beta wave function. Then we had the C sigma, and then we had the S11. You just replace the S11 by the S2, and it's the same story. Okay. So now I can guess where we're going. So if you have a general state of this form, sine 1, y1, sine 1, yk, 2. Remember, if they're all 1, then the scattering is actually trivial. So these are fermionic. So the scattering phase is -1. That's just because these are fermionic objects. But okay. Okay, so we're gonna make the choice now. So before the psi alpha, the alpha 1, alpha equal to 1, alpha equal to 2 are on equal footing, but now we're gonna make a choice. We're gonna prefer the psi 1, and we're gonna view this as a level 3 vacuum. This is a level 3 vacuum. The fact that this thing happens to be equal to -1 means that means that what you would write as analog of the two with two scattering phase. So okay, this notation is slightly confusing, but let me try to explain this. So the fact that this is equal to -1, which is accounted for by the fermionic statistics, means that there's actually no level 2 scattering phase among the psi ones, right? So earlier, so this is not to be confused with this S2. You see, this S2 is a two-body matrix that has a full matrix. This is it's a 4x4 matrix. This is a single scattering phase. This is the analog of this S11 I wrote earlier, which is also a scattering phase. Remember, this S11 was A12, right? So that's sort of kind of the thing that makes up the vacuum for the next level. So the scattering of those things before level 1 was A12, now it's just 1. So this is a simplification. Now I think there are some group some representation theory expansion of this, but I actually I don't think I can explain why this is equal to 1 from kind of just representation theory point of view, but I think there exists some representation theory reasoning why this should be equal to 1, but here it just comes out of calculation. It's just what it is. It has to do with the fact that, I mean, it's not something surprising. It has to do with the fact that, as I said at the beginning, I could have started with psi 1 instead of the phi 1 to define a level 2 vacuum. That is kind of related. That is related to the fact that this is equal to 1, but or m plus n equal to -1. But I don't think I can give you a very precise explanation that do not appeal to a explicit calculation. Okay, so we have this, and then you repeat this, following the same procedure. We're going to be able to talk about one particle excitation at level 3, which will just be psi 2. That's the only thing left. So you can imagine what happens. So you're gonna replace one of the psi 1 by psi 2, and then there's gonna be some coefficients. Actually, I still need to write it. So some k from 1 to capital K, dk. This is a new object now. W yj times psi 1 y1 psi 2 yk. So one of the psi 1 is replaced by psi 2. The rest is still psi 1 y capital. Sorry. Okay. Maybe it's hard to read. There's a lowercase k, and there's capital K. Capital K is the total number of level 2 citations, and now viewed as the providing the vacuum for level 3, so that's the one particle excitation at level 3. So the d function, just like the ck function, is now a new object. It's a new object you have to solve.
It should be W on the left.
Oh, sorry. Thank you. Yeah, sorry. Right. So W is a new spectral parameter. So let's recall. So level 1 we have the spectral parameter either P or x plus minus, up to you, what you call it. Level 2 would have the y spectral parameter. Level 3 you're going to have the W. Okay. Now, let me erase this. So the answer for the B is going to be that everything is very similar to before. Yj is equal to, so before you had the ck y pk pj, now you have dk w yj. Going to the next level. So there's a new function g w y k product L from 3 to w y L. And so you play the same game, you can solve for all of these. I won't write the detailed equation now, I'm just gonna tell you the solution. So it turns out that GWYK is equal to W plus I over 2H over W minus Y minus 1 over H plus I over 2H. And S32 WY is equal to W minus Y minus 1 over Y minus I over 2H over W minus Y minus 1 over Y plus I over 2H. Okay, so you play the same game, you'll be able to solve these. Where again, let me remind you that up to now, W was undefined, but once you find the solution can be written in this form, it depends on the, so we can define W such that it enters the expression in this way, right? Finally, if you analyze the two particle states at level 3, two excitation level 3, you will find the scattering phase of level 3 excitations among themselves, which are called S33. So S33, which is now a function of W1 and W2, will control the asymptotic the two-body wave function that diagonal Hamiltonian. This turned out to be now something turns out to be simple W1 minus W2 plus I over H, W1 minus W2 minus I over H. So and then actually I'm done. Okay, so yeah, at higher level you go, the simpler it becomes, and then we're done. So what have we done so far? So what have we done so far is we have discovered some kind of resolution that represents the Magnum kind of scattering states, the diagonal Hamiltonian, in terms of these level 1, level 2, level 3 wave functions. So this essentially kind of abelianizes the problem because now at every level you can just impose the periodicity condition of the wave function of that level, which is the standard kind of simple Bethe-Ansatz kind of expression. So now let me write down the analog of the Bethe-Ansatz for these using this nesting procedure. This version of the Bethe-Ansatz equation is sometimes either called nested Bethe-Ansatz equation or Bethe-Yang equation. I guess this attributes to C.N. Yang's original work on a special example of this. So for our SU 2 spin chain, the dynamic spin chain, it looks like this. So this just follows from demanding level 1, level 3, level 1, level 2, level 3 wave functions are periodic. E to the I pkl is product J not equal to K to I'll call K1. K1 is the number of level 1 excitations. But earlier I called this M, so but let me now use a more unified notation. S11 Pj Pk product L from 1 to K2. This is the number of level 2 excitations. S21 Y L, okay, where K runs from 1 to capital K1. And then level 2, I have 1 equals something, product. So there isn't this momentum to the L power anymore. J from 1 to K1, S21 Y K prime Pj. Inverse product L from 1 to K3 S32 WL YK prime, where K prime ranges from 1 to capital K2. And finally, 1 is equal to product j from 1 to k3, S3 to wk double prime yj inverse product L not equal to k double prime up to k3 S33 WL WK double prime, where k double prime is ranges from 1 to k3. Okay. Remember that S22 was 0, so that's why that there's no 22 showing up here. That's some weird simplification for the system. Okay, so yeah, well, once you have derived this result, so this is kind of the key. This is the sort of the most important set of equations. Once you have this, then you will be able to just diagram this and solve the spectrum in that. That's another way you can complete. Now, of course, here the analysis is restricted to this SU to come two system sort of on the left. I have to combine the right SU2/2. You have to tensor together the two sectors. That can be done. It's just that you write the full equation is kind of very long. So I will not write in that completely explicit way on the board, but it's easy to tensor the left and right SU2/2 together. You just tensor together, the different the higher level scattering phases. Okay, there are a couple of further subtlety that's kind of special to this dynamic speed chain in Engels-4 superMNOs, but I think I will not mention that right now because I think this is already kind of pretty heavy for today, and I think we're also it's already 2 o'clock. So I think I will. Okay, let me just say in words. We'll discuss this in more detail next time. There's something called string hypothesis. So the string hypothesis has nothing to do with the string of string theory. This is referred to the so-called beta string. So the idea is that so where are we going with this? Our interest in this beta-Young equation isn't just to try to solve for the most general eigenstate, and that's something you can try to do, but we have a very specific application in mind. We're trying to diagonalize the system on a very large spatial circle for a very long closed speed chain. And we want to find all states, and really sort of all states. In order to solve for the actual equations, you want to know sort of all the. So these equations will have a discrete set of solutions, right? You remember even in the simplest case of Balano, it has a discrete set of solutions labeled by some integer quantum numbers. Those are going to be the energy eigenstates on a very large circle. We want to get all the states so we can calculate the final temperature free energy or Brownian function. And then we're going to use this mirror TBA, which is like a double Wick rotation, to extract the spectrum system on a small circle. So there's going to be that double Wick rotation magic, which will come later. Now, in fact, in order to do this mirror TBA, we're going to be considering the beta-Young equation not for the ordinary magnons, but the so-called mirror magnons, which are related by double Wick rotation. And that essentially means I'm going to exchange the role of momentum and energy with a factor of I in front. Right, so otherwise it wouldn't make sense because our system is not relativistic. So you cannot just literally swap space and time. You're not supposed to do that. You only swap space and time for a mirror theory, a mirror model, if you wish, an integral model, where the magnons have different, has the energy and momentum swap of the factor of I. But the scattering phase would be the same scattering phase. It's just that they're viewed as function of different momentum variables. We'll discuss that later. Now, in order to apply this procedure, though, in order to get the free energy, you have to calculate the partition sum over all states. And so this is usually done through this so-called thermodynamic beta ansatz. However, the usual thermodynamic beta ansatz require that you know that you have accounted for all the species of particles. Now, in this context, it's true that we have all the elementary magnons taken into account already, but they can form bound states, which generally correspond to complex spectral parameters. So if you look for a solution to these equations, you have to ask about the possibility of having complex spectral parameters, because even in the case of just the level 1 magnum analysis, there's a possibility that magnons can form bound states. The bound states will be described by a wave function that is normalizable. So but the individual particle momentum will have will be complex so that it falls off. So the wave function will be normalizable with back to center of mass. Now, so that's the actual layer of complication. That is to say, if you want to find the general solution to the equation and find the energy eigenstates, it's not enough to only look for real solutions. You have to look for potentially complex solutions, and that's a hard problem. In general, a priori, it's a hard problem because you may not know exactly where you're supposed to be looking for on a complex plane. You have to make sure that they actually describe bound states and so forth. So it will turn out that this problem can be solved completely, and this was achieved in 2009 by Archinoff and Frolov. The bound states are gonna be described by the so-called beta strings. So it turns out that the bound state of these magnons, or more precisely for the interest, are going to be the mirror magnons. They're going to involve, like magnons with the momentum, generally a kind of array of magnons with complex momenta. There's momenta lined up in a specific way so that they give rise to a bound state pole in S matrix, in the n-body S matrix. So that's the way that's how you would, in principle, find the bound states. The idea that if you have a proposal for what all the bound states are in terms of the beta strings, and you say that this exhausts all the possible bound states that will contribute to the free energy, that's the thing that's known as the string hypothesis. So the string hypothesis refers to a proposal for the classification of all bound states in terms of the so-called beta strings. The beta string is nothing but a kind of finite array of complex momenta for the magnons that we'll be able to represent in terms of special parameters, which we'll be able to determine. So that's roughly where we're going. But I think we'll defer that discussion to another occasion. Yeah.
I have a lot of questions. So first of all, why is there no S recon one?
That's just the nature of how these equations are built. Because the level 3 is built on level 2, and the previous condition, the wave function literally doesn't care about it follows from the equations. This procedure, there's the kind of by construction, only the adjacent levels talk to each other.
Okay, so when I look at this, I should think of, let's say the first line, I have my level 1 excitation. I want to move it all the way around, so I have to pass it past all the level 1 and all the level 2s. And it would pass level 3 excitations as well, but it just doesn't see them.
That's not the precise way to describe this. I would say that the precise way to describe this is simply demand the level 1, level 2, and level 3 wave functions to be single valued on the circle, each individual, and that's it.
And then
there's just the level 1, the level 3 never appear in the same equation.
Another thing I was confused about, the. In the single state level 2 excitations, we already had site twos. And then when we did the level 3 excitations, we also. made site twos.
We had the side twos there, but we're not, but that side two is not used to build the level 3 vacuum.
Yeah,
It's the same way as how the phi 1 was used, in level 1, right? So at level 1, you can also talk about the size of level 1, but we use a phi to build a vacuum. It's the same logic as there.
okay. I guess my question is, in this case, we never see the. Phi twos as like a basic excitation of any of the levels.
That is correct. Now, let me see. So, the phi 2 should have been already accounted for with the psi 2. Because the phi 2 can roughly speaking be viewed as a psi 1, psi 2 bound state. Now, where would you find that particular state? Let me think. If you consider a psi 2 excitation level 3, which means the level 2 description, the psi 2 buried in a bunch of psi 1s, right? Now, that wave function contains psi 2 somewhere in position space. However, the asymptotic representation doesn't, I don't need to talk about phi 2 directly. So phi 2 is somewhere. So when the psi 2 moves to be on top of the psi 1, the psi 2 the phi 2 will participate. But in this asymptotic basis, I don't have to speak of phi 2 separately. And somehow, somehow that's enough.
One last question. I didn't get to ask it before you erased it, but for the level 2 in state of the single phi 2 excitation, we had this sum, and then you had the CK Y1, a CK Y2, and then you had the F Y1, Y2, PK.
Yeah.
And my question is, should I think of that, we're just defining some basis, or is there some assumption that goes into saying that that is enough of a basis?
Oh, yeah. That was an assumption. You can do some counting. So that was essentially the same game as the previous stuff. It's similar to the previous ansatz. Indeed, that was in some sense the most non-trivial assumption, right? You can, you can count to convince yourself that it provides a complete basis, but it's not. I don't have any simple way to explain this other than staring at the equation for a while then you recognize. I feel like by nature this is a subject that requires a lot of meditation. It's not easy to absorb.
So at the left-hand side of these Bentham equations, there are at level 2 and 3, there are ones at the left-hand side, right?
That's right.
But shouldn't there be like the one particle wave functions that monodrom as you go around the chain?
No. So the idea is that that has already been accounted for by the ansatz. So there isn't any additional phase on top of that.
But we were solving for these F's, right?
Yeah, but okay. No, you can think of you can think of this as saying that sort of the plane wave like wave function has already been included in the F. So it's already accounted for somehow. Yeah, that's all I can say.
Okay, I have another question.
Yeah.
We had an S2 with the alpha and the beta indices. And
That does not show up here.
there's no S3 because the level 3 excitations are only the same.
Correct. That's also correct. And also because I can term it to level 3, there's no level 4, thankfully. I think the fact that term to level 3 has to do with the specific group SU2/2. If it were like SUN, you have like n-1 level or something.
So if you're scattering in some theory of like infinite dimensional symmetry or infinite limit and beta equation.
Yeah. Yeah, so there's actually, there's this German group headed by Karowski. He's retired now, actually. I don't know even know if he's alive, but I actually invited him to visit many years ago. But they have used the nested patterns to study like SUN gross Neville model in 2 dimension. So for the form factor is a very very advanced kind of integrability technology, and you can do a lot with it. Yeah, so these equations are going to be essential. Okay, so now this equation looks like okay. Let me say make another comment about where we're going, because at this point you might feel like you might get a headache from staring at these equations, especially if you actually spell it out. And I wouldn't blame you, right? These equations, when you take the thermodynamic limit for the mirror model, it will turn into the mirror TBA, which can be repackaged in the Y system. Later, this Y system will undergo further repackaging into the quantum spectral curve. There will be some very, very elegant structure that emerge out of this. Okay, at this point, it looks like kind of a mess. Okay, I mean, there's already some magic, right? This formula, this matrix, this scattering phases seem to be simpler than they have the right to be. But later, we'll see that there's a kind of tremendous amount of kind of hidden structure in this equation that would emerge when we do this mirror TBA business.
So can this problem be like reformatted by taking the mirror TBA and taking it out to infinity and get some simple problem or something? Because it doesn't use structure.
Well, simple is a matter of perspective. In fact, when you turn this into mirror TBA, of course, you will not have this kind of discrete products. You have integrals, right? Roughly speaking, like the mirror TBA is like you. Okay, let's say this. So you need to study a statistical mechanics problem, which is to consider all the possible states that will solve this equation, and you need to count their entropy and find the temperature, and then you write some kind of thermal partition function, and then let's say you kind of extremize the free energy, and you find the you find the free energy of the system in the thermodynamic limit. In this procedure, okay, I think it's still hard to explain this without setting up the formalism, because I have to introduce like the density of states, the kind of in terms of the kind of occupation kind of level density, because when you take the log, there's going to be some integer that parameterizes like the level of your quantum states. I have to introduce some kind of level density, and I have to solve that for that in the thermodynamic limit. So after all that sound and dense, the thermal free energy problem gets turned into the TBA equation. The TBA equation would be some integral equation that involves essentially the log of these phases as kernels in these integral equations. That equation is still a mess. It will follow from this. That equation is still quite complicated, but then it turns out that they can be kind of sorted into this Y system equation. That by itself is actually not enough. But it turns out that let's see what's the way to say this. It will be very important to explore the analytic structure of the various kind of functions involved, which are this pseudo energy that come from the level kind of density. and the continuation would be the special parameter. The special parameter will be this y's and w's. That somehow will play an important role. Yeah, I mean, there's a reason why the subject is not easy to penetrate, because without knowing the details, you really cannot understand what is going on. So that's just the nature of it. But usually when you hear talk by like Gromov or someone, he will never explain this in his talks, right? He will just say, "Oh, here's the quantum social curve, and here's how you can use it," but never mind where it comes from. But this is necessary to understand where it comes from.
How well do people know about the solution for this Sebastian equation?
How long do people know?
Oh, well, because like I think this is basically determining the spectrum of your scalar dimensions in equals to 4 of like single trace operators.
But in the long chain limit.
Yeah, but like I'm thinking about like, do people find dipole operators for this?
No, because this is in a strict single trace. So long, the chain is long but small, still small compared to n. You never find a black hole like this, right? We're in a different regime. We're in the regime where we're doing free string theory here. All this is free string theory. We're not even talking about string interactions. This is all just free string theory in ADS 5 times 5. But even that, as you see, it's a complicated problem. Well, at least up to now, there's no indication that you can learn anything about black holes from integrability. But there could be surprises. There's no nobody has proven that you cannot see it, but as far as I know, there's no expectation that you should be able to see. Because like you're expecting that the black hole, arise in a regime where you have order dimension of order n squared, and there's no meaningful distinction between single trace and multi-trace or determinant operators. So certainly in a much more complicated regime.
One question. Okay, so when we wrote the equivalent for going for the single level to excitation with the CK and the F instead of G. Yeah, this equation relating, well, we just considered the single neighbor swap. We had the relation of these creation operators, and when we swap them, we would pick up the G's, H's, K's, and L's from the original S matrix.
Yeah.
In this case, when we do it, we have psi 2s that can swap with the vacuum psi 1s, and we swap them with this S2 matrix, not S2 comma 2, just S2, which is a matrix.
Yes.
It only involves psi 1s and psi 2s. That one also does not involve phi 2s or phi 1s, even though at the level of the original S matrix, having a psi 1 and a psi 2 would involve phi 1 and phi 2.
That's correct.
This works out only because that's S2 is only between the sides.
Yes.
And that's somehow because we're building it on this already complicated.
That's exactly right.
Okay.
Yeah. So essentially, somehow in this nesting procedure, once you go to the level, you can forget about the previous level and just work at that level.
Okay.
Yeah. It's yeah. Somehow it's a structure that applies to large class integral system, but it's completely unfamiliar to anyone who has not dealt with integrability. It's just some very weird thing. But somehow it's quite ubiquitous in integral systems. Like in the 2D Hubbard model, they have something apparently very similar. That's how they were able to kind of solve this problem so quickly in like between 2007 and 2009, because like somehow like some condensed matter people that do integral spin chain have already seen very similar things in other models. I mean, otherwise it'd be hard to kind of invent all of this within like a couple of years.
So what is the status of this in like other backgrounds, like ADS3 equals S3 equals?
So ADS 4 times CPU3 is almost the same, actually. It turns out that things are always a little bit more complicated, but not by much. So the details of the structure is a little different because it's just because the symmetry group is different, but that's sort of like the only difference. This H parameter which enters the magnitude dispersion relation, right? That's how the Topf coupling enters. So here the H is just like the square root of Topf coupling. In the ABGM, the H is related to Topf coupling in some complicated way. That function is only possible to determine by comparing with the results of localization. So essentially by thinking about the Wilson by studying okay, so you can kind of relate the spectrum determined by the spin chain to the normal summation Wilson loop at an angle, and that can be related to some calculation localization. So there's some kind of non-trivial story there. That actually came later. This is what I think was only known in 2013. This came much later, maybe 2013 to 2014. Because for a long time that the function is not known. So in the ABGM theory, there would be something that analog of H, but how it's related to the Chern-Simons level was not known until later. But that's just one number. Apart from that, everything is more or less the same, but the detailed structure is different. Like the shape of the Y system looks a little different because the group theory structure is different. ADS3 is a completely different story. ADS3, there's some very recent kind of work in progress of people like Sfangini and Stefanski and others. What I was told is that, of course, in the pure NSNS, it's a solvable system. Pure RR is expected to be integrable. And for the mixed flux, they think is also integrable, but maybe for some like limited restricted sector. I don't actually know. I think that they believe it's integrable even with mixed flux, but I don't know to what extent that has been tested. I mean, a part of the difficulty is that there's no data to test against. I like Engels force super ml, so we can compare to perturbative calculation, which is very non-trivial. In the ADS3 case, there's you cannot check against the CFT. At least, I guess nowadays there was this approach from Gabriel and Gabor Kumar, right, from the symmetric product overfill, the perturbation theory. They seem to also see integrability. But there was just this paper like 2 days ago by I think Sfangini and some collaborators that dispute their results. Well, I don't know whether they can call them as disputing, but they say they tried to reproduce it, but they couldn't reproduce that some aspect of it. So I think that the status is still kind of not settled. So I mean, in the ADS3 case, I think right now the status is that the integrability people have already designed this quantum special curve. They have proposed the quantum special curve for the ADS3, but there's not much data from the CFT side to compare with. It's just a hard problem. This perturbed symmetry product orbital.
Is it like harder perturbation than the DVV we're doing, or
It's like harder.
It's like marginal, no?
It's marginal, but the marginal doesn't mean it's easy. You have to kind of go to high order, right? So then they're looking at the kind of the 12 limits. So it's a different flavor. It's not like major string theory. We're doing something different. Yeah, okay. Maybe we should write up. I need to go to the thesis defense soon.
Well, I guess in the planar limited it would be simpler, no? Because they invent some like diagrammatics for this limit.
So who invented that?
Like Rastelli or something.
Oh yeah. There was this thing, but they didn't go anywhere at the time. And at KITP last year, Gabriel was talking about this recent work, and people ask, what is different from what Rastelli et al. Did? And basically he said that it's the same thing, it's just that we're more determined.